This lecture is all about using everything that we saw in the semester to solve a problem that you care about. Before we get into the details of the lecture, just a reminder about all the wonderful things that are due. There's a homework due today. There's an exam, not due, you have to show up. There's an exam on Wednesday, and there is a project which I'm sure all of you have finished. That's due on Friday. Are there any questions about homeworks? You had a question.
Yeah, it's about the M step for the, like problem 2, and you want the E and M step. How much do you want us to actually maximize this thing? Or, because I don't even know how to compute the expected value of this. It has like a random variable in the top of the sum.
No, it does not. It should not. The expectation is over all labels. Right? So you know the number of labels. What was it? Is it some stores, Smith's and Trader Joe's? So the expectation is just sum of two things. Probability that it's Smith's times the log likelihood for Smith's times plus the probability that it's Trader Joe's times the log likelihood of that. So this was a hint I gave the other day. The optimization problem, maximization step should actually be very easy. In fact, there were a bunch of people in my office hours, and I'll tell you something. I told them, if I just give you the optimization problem as a question in calculus, you should have been able to do that in high school. So really, the tricky part of this question is not so much solving the optimization, but writing down the question. If it is difficult, that's a very simple sign that's a somewhat not very that's an unambiguous sign that you made some mistakes. So there is no random variable at the top of the sum. There's a remote question.
Can you work through problem 2.4 with the class?
Can I work through problem 2.4 with the class? So you want me to solve the homework in class? Are there specific questions though?
Let's see.
For the graph of negative log likelihood for the original data, it doesn't look very smooth.
It's not going to be very smooth, but it will, in general, have a downward trend. It won't be. It will be jittery because you're doing stochastic gradient descent. In fact, I'll have a picture of what it should not look like later today. It should go down. This is a very common error that happens. It happens to the best of us, and that only means that there might be some bug somewhere in the place where you calculate the negative log likelihood or in your learning algorithm, and don't sweat it too much.
Because the same program is actually giving a right curve for the expected curve for the scale data.
Oh, good. So
that one is pretty unexpected.
So this actually might tie to the question that Michael had about numerical instability. You are doing log of 1 plus e power something, which means if that something is very big, e power something is also going to be very big, so it doesn't matter, you're going to run into infinities, and you might have some quote-unquote hacks to fix that, and that might lead to odd behavior of your expected log likelihood. So,
but I have hacks for both of them.
You have hacks for both of them. Yeah, but then the problem is the e power something, the exponent, the thing on the exponent might actually not get very large for the scale data. I'm almost certain it does not. Whereas for the original data, it probably does.
Yes, it does, but the approximation is like pretty straightforward.
The approximation, there's a discussion on the mailing list, right? Just keep an eye on that approximation, see if how often that fires, and that might actually help you diagnose your answer.
Yeah,
so I see many hands up, so you first, then I saw you, and then you.
I was just about to say, I keep track of how many overflows I do, and on the non-scaled data, it's in like the tens of thousands.
Right, which means you're losing fidelity quite often.
Yeah, And on the scaled data, it's almost never happened.
Yeah, not surprised. Yes.
So, I mean, do you have any tips? Because when I try to calculate e to the power y w transpose x, I'm frequently getting overflow.
Right, so one common, and not, I'm going to write on this just, one very common trick is to notice that the thing that we care about calculating is log for some z, right? Now when z is very, very large, this is approximately equal to z, right?
Right.
When the actual value of z is very large. When z is very, very small, this is approximately equal to 0. When z is negative infinity,
But if you were to underflow, then it would go to 0 anyway, right?
it will go to 0 anyway. So that's, underflow is less of an issue, overflow is definitely an issue. And this is one way of dealing with that. Now the question is, you need to define what is very large.
Larger than overflow.
Larger than overflow is one answer. Another one is 12. I don't know. So you have to be careful about what that number is.
So, alright, so we can just equate that to z.
Yeah, yeah. Just if you have when you're calculating this value, if z is greater than some number, just use.
But the log expression for in the derivative,
Yes.
we directly have an e to the power z expression in the base.
How do you have a? You don't have that. You
For
should.
the gradient.
Huh?
For the gradient?
You should not have an e power something. You should have an e power something divided by 1 plus e power something.
Right, yeah.
Now when z is very large,
So, like, the expression that I get is xy and e expression upon 1.
right? So
And I
you
take
have
it down.
you have an exponent in the numerator and an exponent in the denominator.
And I take it down, so I'm eventually just left with
1 basically. When z is very large, that quantity becomes 1. E power x divided by 1 plus e power x, when x is very large,
Okay.
tends to 1.
So, okay. Well, it's e to the power minus something, and
Then it
when
becomes
I do
0.
it becomes like some expression and divided by 1 plus e to the power z.
Right.
Right? And the numerator expression doesn't have any term.
So you have something,
Like xy upon 1 plus e to the power.
something like this.
Yeah, and in the numerator it's just x and y.
Now, okay, sure.
Right? Because,
Okay.
Yeah.
Yeah, yeah. So when
E though.
Mhm.
you can use a similar sort of an approximation. When z becomes very, very large,
Mhm.
this whole term becomes very large,
Right.
which means this thing, the whole thing becomes 0.
Zero.
When z is very, very small, negative,
Right.
this disappears.
Okay.
Right?
Alright.
You had a question.
Well, it might not be as relevant anymore because it sounds like there's a few things going on, but I just wanted to say that when I was doing my plots, I had to play a lot with the scale and like they had to be on separate, like it took me a few minutes to figure that out because it made a big difference for if you could see the
Okay,
relationship.
okay, that's a valuable tip. Alright, thanks.
Are we expected to have a higher accuracy on the scale data?
What I expect, okay, so first of all, you're going to let your data dictate what happens. But I would be surprised if the quality of the results, the trends, are very different from what happened when you did SVM. So in SVM, most of you saw that scale gave better performance. I anticipate a similar thing here.
Yeah, I got similar, about the same amount of accuracy before without the kernel in SVM. So I had like 80%.
Right, right.
But it was weird because it's consistently, the scaled one is like 3% lower than
In the logistic regression?
in the logistic regression.
That's
Yes, I also observed as the original was doing much better.
okay, that's interesting because this is one of the few places where logistic regression and again another point of huh?
I'm getting really good accuracy on scale, but not very good.
Okay, we have a contradicting report at this end of the room. Anyone else going once, going twice? Okay, so there seems to be some mismatch, but my expectation, I'm not saying this is how I'm going to grade it, my expectation is closer to what you guys observed, because I would be surprised if the loss function makes such a big difference.
The negative log likelihood on the scale data, for me, I'm seeing a plot that's like very monotonic, it's decreasing.
Okay. For the other one, it's spiking.
Yeah.
That's exactly what many others seem to observe. So go with it.
All right.
Right. Was that another question from the remote end of the thing?
No. Oh wait, you just posted one. Can we get solutions for final exam study guide?
Yes. Well, most of the solutions are actually on the slides. If you look at the study guide, they are actually just saying prove that all the things that we proved in class. But we'll try to write one up and put it up before the weekend. And also, that's a good point, a good thing you mentioned that. There are 3 review sessions that we've planned for the final exam. There's one tomorrow, one on Monday and one on Tuesday, and please take advantage of this. The TAs are spending a lot of time on this, so do show up.
What are the times on those?
It's on Canvas. So.
Is the final comprehensive?
What?
The final, is it comprehensive?
It's everything that we did from learning theory. Everything that was not there in the midterm. You had a question.
I was just going to make the observation. So one of the things I was thinking about was, depending on your initial guess for W, it's going to determine like the shape of the curve for the negative log likelihood. Like if you make a really good guess for the initial W, then you're really close to the minimum.
Well, sure.
And then you'll just maybe see like some jitter.
Right. That's valid, but
because for my W was, and I could have been way off here, but my W was pretty close to 0. And so if you start at 0, then you're not going to see like a big huge decline.
Okay. Sure. There is nothing inconsistent about what you say. It makes sense. Did I see another hand anywhere?
Can you post a couple examples about expectation maximization?
Okay.
Solutions?
Yes, I'll post something. Yes. Probably I'll do that for what do you call it? The naive base, sure. Other questions? Okay, we're going to change, we're going to reduce the technical content a bit now and move to step back and look at the big picture again and talk about how we can use everything that we did through the semester to build an application. In particular, the main point of today's lecture is about all this is fine, but how does machine learning, how do I change my software engineering practices if I'm using machine learning? The way I like to think about learning, and I'm not the only one who thinks this way, the way I like to think about it is I want to write a program. There's some program that I need to write, except I just don't know how to write the program. If there exists some system, an oracle, nature if you want, that can give me examples of inputs and outputs, and I want to write a program that mimics that. And the goal of machine learning is, I don't know how to write the program, instead I'll write another program that learns to write programs. So, which means really, it has to fit inside some application. Which means everything that we know about software engineering kicks in. We need to know how to debug and all those things. So we're going to talk about that because it's one of those things that's really important, and the way we debug machine learning is sometimes quite different from the way we might debug other programs, and everything that we learned in this semester actually contributes to some sort of intelligent debugging. Everything here is based on stuff that other people have said, stuff that I have gone through myself and seen and that I've heard. There are a bunch of papers that I've pointed to on the class website. Do take a look at them. These are not technical papers. Mostly they talk about how do you make machine learning work in the world. In particular, I'm going to talk about three different topics. One of them is how do you diagnose mistakes in your program that involves machine learning as its center. The second topic I'll talk about is how do you do error analysis. Error analysis is slightly different from diagnostics. Error analysis talks about if my program makes a mistake. If my classifier gets, as some of you pointed out for your the astronomy data, it only gets 80%, how can I make it better? How do I analyze the 20% of examples where it makes mistakes and make the classifier better? And I'll wind up the whole thing with some thoughts about how you might inject machine learning into your application. So let's talk about diagnosis. The general setup is, so let's say you don't like spam, like most of us, and you don't like any existing spam detector, so you built your own. You use some classifier, you use some features, and obviously, I mean, the one thing I expect from you for sure is that you follow all the best practices. You do cross-validation, you find the best hyperparameters, and at the end of all this, you find that your classifier is only, 75% accurate. How do you fix it? Any ideas? How do you make your classifier better? Did you raise your hand?
I was, but I don't have any ideas. I was just going to say, my partner and I on our project was having this question about, we get an accuracy rate for the test set and we don't like it, so then what?
Then what? Exactly. Then what? And many of you are actually facing this in your project. So first you
try an ensemble.
Try an ensemble. Why?
Because you get better generalization.
Okay, but how do you know that you should try an ensemble?
Because this isn't working.
So let's say that but what are all the decisions that you made to come to a spam detector? All I gave you were a bunch of emails, and you produced a method that takes an email and says spam or not spam. There's some magic that happened in the middle, and every step of that magic could be at fault. So
my first initial reaction to this, and it depends on how many samples we would have, but I just try a feature expansion and see if we got better results on that.
Okay, so you play with the features.
Like a kernel just
playing with the features again. Any ideas that don't involve features?
Well, what I was going to ask is, if we're doing, like, presumably we've got some training set and we have some fixed test set.
Sure.
This is all that we've got.
Yes.
And if we're trying to improve the accuracy on our test set by making all these changes to what algorithm we're using or something, are we starting to learn the test set?
That's a very, very good observation. If you run many experiments on the test set, you are actually fitting the test set, which means you are actually hurting generalization by overfitting not only the training set but also the test set. So that's a good observation, which means all your accuracies and all those, the best practice is always look at cross-validation accuracy rather than having your test set. Don't look at your test set. I mean, you should not let your classifier see the test set, or even you. What I do personally is many times I compress the test file and don't write a reader for it, so that even accidentally I don't point my program to the test set. I saw another hand.
I forgot what I was going to say.
Okay, I saw another hand.
Are we assuming we can't get any more data, or assuming that we can't?
No, I have no idea. You are a software engineer who knows machine learning. I am, your manager, and I say, I've heard you've taken a machine learning class, make my spam detector better. Do whatever you want.
Because one of my thoughts was, depending on what features you have, maybe they're not sufficient. Maybe you're missing out a couple of features that are key to learning it better.
So you are going to try out more features. Okay?
So you theory 5% is good enough.
Is it good enough? I don't know. Okay, how about 60%? How about 51? Okay, your classifier now gives only 51.
Okay, you can use error booster.
Okay, you can use a different learning algorithm.
Yeah.
Okay? One more and yes.
Well, if just trying to do an ensemble of like regenerating the the machine learning algorithm I already wrote, and like using different hyperparameters to get an ensemble of several different learners.
Yes.
If that didn't like raise me up to a sufficient accuracy, say like 90 or something, I would probably try to find a completely different machine learning algorithm to do a spam detector and then ensemble that with my one I had before.
So, to vaguely summarize what you said, you'll change the learning algorithm.
Yes.
You said kernels, so you change the features. So the general consensus has been you change features and you change your algorithm. Last one.
I'd also look at the data. Is it well spread out? Is it representative of what will be in the real world, or is it kind of skewed? So is your test set...
How do you fix it? Let's say the data is skewed.
Say the data is skewed, you maybe collect more data, or you can say, okay, how, we could try to do some analysis on the data and say, could we kind of do costs, raise the cost on some of these examples?
Okay.
Or
right.
can we throw some out so that it's more balanced?
Excellent.
Is it a good idea to analyze where the classifier is making mistakes or why it's making mistakes?
Yes. You've covered a lot of what I want to talk about today, so let's actually take all these ideas and talk about how to use it. So, the general classes of methods to improve your model: get more data, change your features, change your algorithm. That basically takes care of everything that you guys said. You can use more features, you can use less features, you can use better features, you can use different features. Or, you can train for longer, you can train with a different algorithm, you can use ensembles. You can play with regularization, overfit, avoid overfitting, avoid underfitting, and all those things. There are so many options that it's very, very tedious if you don't have an army of grad students working for you. So, in some sense, one of the things that I want to focus on is how do you diagnose mistakes so that you know which of these things to do. Should you use more features or less features, change the algorithm? How do you diagnose the output of your classifier? Okay? So, if you know where the problem is, maybe you can then try to fix it. Some kinds of problems, and these are things that should not seem awfully unfamiliar to you. Your classifier might be overfitting or underfitting. You've not run your learning algorithm long enough because you're not tracking the objective, or maybe because you don't have enough time. Your loss function is not a good enough approximation of the true accuracy you're measuring. Remember, we are many of our learning algorithms are risk minimization algorithms, and all of them effectively build these surrogates for the 0-1 loss, like Hinge or Logistic or Perceptron or Adaboost. And maybe that the one that you chose, maybe the specific loss function you chose does not actually approximate the 0-1 loss well enough to do something. So let's look at some methodical ways of detecting these various approaches. Just to remind you, your classifier overfits when your training accuracy is always higher than the test accuracy. In other words, you have a model that explains the training data so well that it only explains the training data. The classifier that overfits the most is a table lookup. Just put everything in your table, and when a new example comes in, you check the corresponding label in that table and you return the answer. If your table does not have that entry, then you toss a coin. So your generalization error is basically dominated by a coin toss. That's a classifier that's wildly overfitting. Other extreme is underfitting. Underfitting is when your hypothesis space is not rich enough to capture your function. There is no function in your set that can even represent the true concept. Yes?
We could have underfitting too if you don't have enough data.
You could have underfitting if you don't have enough data, sure, yes. One way of diagnosing overfitting and underfitting is to plot something called the learning curve. Very related to overfitting and underfitting are bias and variance. I'm going to use the language of bias and variance. So you vary the size as you train multiple models for different training sizes, and you can plot the training error. In general, this is just a cartoon picture, so I don't necessarily expect training error to keep going up, but in general what you might observe is that when you have very, very few examples, your classifier can explain those examples very well. Because if you have only 3 examples, probably your model is, your hypothesis space is expressive enough to just remember those 3 examples. As you get more and more data, the classifier settles into some training error. At each step, if you plot the test error and you notice the test error goes down, then the first observation is that adding more data helps. But that's not a surprise. Adding more training data helps, and we know that from pretty much every theorem that we saw. What is interesting is the gap between the train and test error is very large. And it never seems to, the gap never seems to, even at convergence, the gap is large. That means your model is overfitting the training set. It gets low error on the training set, but the test error is never ever going to go low enough. This picture here is a classic indicator of overfitting. Yes?
Is this testing error of cross-validation?
No. Well, yeah, cross-validation is a surrogate for test error. Yeah, sure.
Right, because you said not to look at your test,
yes,
your actual test set until you settled on something to use, right?
Yes, yes. Okay, so this is, if you plot these pictures, then the learning curves, then you might be able to detect high variance. The other extreme is underfitting or bias, high bias. This happens when your best, both the train error and the test error are really high, even at convergence. Training error does not, the test error clearly is not going to go below the training error, but both of them are unacceptable. That means your class of functions that you are considering does not have the capacity to represent what you care about. It may converge to the same thing, which means they are actually meeting. Both your classifier is getting to the learning algorithm is finding the best classifier it can, even with the lowest possible test error is not acceptable. High variance is often observed with very complex models. Models that can express, or very complex hypothesis classes that can express more complex functions. High bias is observed with simpler functions. Functions that can't label too many functions, that cannot capture many functions. So, in the context of all these, this laundry list we had, typically what happens is if you have more training data, it helps counter overfitting. Because if your training set consists of every possible example you can ever see, then overfitting that is not bad, because getting a zero training error on infinite data means you're getting a zero training error in general. So more data tends to help combat overfitting. Adding features tends to combat underfitting. Why? Because you're making your classifier look at more sensor output in some sense. You're giving more space for your classifier to move around, so adding features tends to combat underfitting. And conversely, removing features tends to combat overfitting. That third option there, use other features, is just a wild card. That simply says, maybe your features are just wrong and try something and work with it. Regularization is this knob that we had. You could, in a very clear way, for a given feature set, you can trade off between overfitting and underfitting by controlling the C or the sigma parameters that you guys have been doing in your assignments. Questions? Yes?
One thing that my partner and I were having a discussion about was the idea of a test set in overall, because we train a classifier, we get a classifier, we look at the we look at the test error, and we don't like it. But it seems like if we should never touch it until the very end, then basically we have either we win $1 billion or we just die because the test error is really bad.
Well, not quite, right? Well, not quite, because you're not going, even though you're not going to look at your test error, you have your cross-validation error. Your cross-validation error is a surrogate for the test error. In some sense, the test error, the test set itself, is supposed to be a representative of future examples, that your learning algorithm has not yet seen. In fact, the learning system, which includes you, has not seen. So looking at the test set is as if you get a peek at the future, which is not right. Which is why you need to somehow use only your training set. One other very common thing that's done is, let's say you are given 10,000 examples for training. You keep like 10% of it aside and call it the validation set, and you keep testing on that set. That's not your test set, that's your validation set. That's not the example, that is not the set on which you will advertise performance. So you could do that. And the cross-validation is just generalization of that. Right? Instead of doing one validation set, you try multiple validation sets. Yes?
Is using the validation set common practice to determine what number of iterations you should
Yes,
do?
it's definitely done. It's very common. In fact, using the validation set is really, it's so common that many machine learning systems actually make it a part of the architecture. Okay, so we kind of looked at how to diagnose overfitting, underfitting. Another problem that might show up, and actually many of you asked even before, through the semester, was how do I know when to stop? We run for 20 iterations, we run for 200 iterations, how do I know which one's good? And one of the most robust ways of doing that is to keep track of the objective function that you're optimizing. Exactly what you guys are doing in your homework right now. Plot the objective function. If I want to minimize some objective, you plot it as the learning proceeds, and just by eyeballing the objective function, or actually to make it more concrete, to look at relative changes of the objective value, you can decide that if the objective does not change by more than epsilon, then I'm just going to stop. So plotting the objective is a very robust way of checking for convergence. But it's not always helpful, because most of us will agree that the classifier has not converged at this iteration right here. But it's not clear whether it's converged here either. It seems like it's still going down. So this is, if the objective converges, then the classifier, you can stop training. If the objective has not converged, doesn't mean that you can't stop training. So it's a one-sided test. But one thing that does happen, and this is related to the questions that came up in the beginning, it helps us to debug. If you're minimizing a function, and the objective goes up and down, and it seems like a wild roller coaster, something is wrong. Either your optimization is wrong, or your, the function that plots this thing is wrong. So if you're doing gradient descent, you need to go down the gradient. The theory says that you're going down the gradient. You have a convex function, which means the objective has to keep decreasing. And yet, if you notice that it goes up and down, that's a problem. Side note is that this does not always hold for stochastic gradient descent. You will see local jitters in the objective. For gradient descent, on the other hand, for full gradient descent, the objective will go down. So if you want to keep track of how training happens, if you want to decide when to run more iterations and stuff, you track the objective for convergence. The other point to keep in mind is, what happens if your loss function is not good enough? What if the right thing to use is the hinge loss, that is SVM, but actually you're using logistic regression and you have to decide which one's better. One way of answering that is just to do cross-validation. Another part of your cross-validation is the choice of the learning algorithm. Another interesting trick is, say you have two objective functions, two classifiers. Let's call them A and B. It could be hinge and logistic. So that gives you SVM and logistic regression. What you do is you train both the classifiers, you run both of them to convergence. Remember, what is the loss function saying? The loss function says, if the loss according to this objective is low, then the quality of the classifier that comes out at the end is going to be good. The loss is simply a surrogate for the 0-1 loss that you care about, the accuracy or whatever metric. But if you observe that A, so according to your learning, if you observe that the optimum value for B is less, which means B, according to the learning, should be a better classifier, because lower objective implies better classifier. If the optimum value for B is lower, but the error of A is better, that means it doesn't matter if you get to the optimum of B. B does not capture the problem well enough, the learning problem. Does it make sense? Questions?
Could whatever algorithm we use be thought of in some sense as a hyperparameter?
Yes. Every tiny change that you make can be thought of as a hyperparameter, but yeah, absolutely, but be very wary of something. If you are going to have a million hyperparameters, then you're really doing learning over the hyperparameters. All the points that we had about learning being impossible apply to that setting as well. So then you'll have hyperparameters for that learning. So in general, keep the number of hyperparameters very low. Be slightly suspicious of claims that say that we have done cross-validation over 5,000 different hyperparameters and found the best one, because I would be surprised if those things are replicable. Other questions or comments? Yes?
Have you ever seen like a serious machine learning application where they actually had a lot of hyperparameters, so they actually had to use a machine learning algorithm to
Yes.
learn the hyperparameters?
Yes, there are a few places where even hyperparameter search becomes a learning problem, and it's not treated as the same kind of learning problem that we've been looking at. They use ideas like sampling. They do random samples over hyperparameter space and try to bias it towards hyperparameters that matter, and some choices maybe don't matter, and they try to discover which of those choices matter and do careful tuning there. And there are a few papers, in fact, that came out even in the last few years which talk about exactly that. Okay, so we've got a bunch of, I've just covered a small set of ideas that talk about how to diagnose errors in your machine learning, in your classifier. Notice that effectively this is really debugging. It's debugging, but not the kind of debugging that we see in software engineering. It's not the kind of debugging where you say that your classifier, not your classifier, your program should produce 13 and it produces 14, so there must be a bug. Because we're not talking about absolute right or wrong, because we're talking about percentages of errors. Your classifier is right 80% of the time, which means it's not very wrong, but it's still wrong.
Is there some way to judge whether what accuracy we are getting is the best we can do?
Unfortunately, that's an intractable problem. Unfortunately, that's an intractable problem because that requires knowledge of the concept. If I knew the concept, I could judge that.
Given the data, is there some way to...
No, given any... not quite, unfortunately. Because when the data, given any data set, let's say you have 100 examples. I can overfit the 100 examples and not know anything. Then let's say you give me 100 examples and you have 50 test examples. Then I can tweak my parameters so that I overfit those 150 examples. Still haven't learned anything. So, as I was telling someone before the class started, I have never seen a linearly separable data set out in the wild. There's always noise, and it's just something that we're going to live with. So, if you get 100% accuracy, I'll mention this much later, if you get 100% accuracy in some system, then you should be suspicious. Maybe you're using the label as a feature. That's a very sure way of getting 100% accuracy. So you should be slightly suspicious of perfect classifiers. So let me talk about another important point which falls under the umbrella of error analysis. Error analysis is different from diagnosing. It falls in the same ballpark of debugging machine learning, but it's a different style of analyzing mistakes of your classifier, which talks by looking at it at a systemic level. This picture is from a paper at in NIPS, that's the Premier Machine Learning Conference. This is from NIPS 2015. I think the poster came up 2 days back. So it's really bleeding edge. And the point of this paper was that typically, even though the focus of this class was machine learning is this important and it's this giant beast that covers a lot of things, in most applications, typically machine learning is a tiny little piece. There are all those other things that need to come into play. So just those of you who can't see it, this is machine learning. There are all those other things that come into play. Like you have your infrastructure, you have the feature extraction going on, you have data collection, sometimes you might have monitoring and some client server stuff and presentation, visualization, analysis and all these things. And machine learning is, the learning algorithm itself tends to be a tiny, tiny piece of this. So if you want to actually analyze how the entire system is doing, you might want to actually tease apart the contributions of each of these pieces. Particularly, at least from the point of view of the learning algorithm, the immediate surroundings are the feature extractors, any pre-processing that you do to your data, for example, scaling. In the last 2 assignments, you've been looking at 2 variants of the data. One of them is scaled, one of them is not, and one does better than the other. How do you know whether you should scale? How do you know how you should scale? So that's basically data transformation. You could do feature transformation. You could lift it to a higher dimensional space, to a different space. Sometimes the feature extraction itself might be the output of a machine learning system. Now that means errors propagate. Error analysis is a broad class of methods that are used to identify why your system is not working in the context of the larger application. So just as an example, my preferred area of research is natural language processing, or at least that's where I look for problems. And the way the general text processing pipeline would work is you have some text, something, I don't know what, goes and gets me the words in the text. Another system looks at the words and the whole text itself and predicts the parts of speech, nouns, verbs, and adjectives. A whole other system looks at the words, the text, and the part of speech and predicts parse trees. And finally, the application that you care about. Maybe it's trying to answer questions. I know that there's some overlap between this class and natural language processing, and I know that you guys are trying to build a system that automatically answers reading comprehension. So that could be your application here. So you have all these pre-processing things, and they finally contribute to this, your machine learning application. Unfortunately, all of these are, they could be ML driven. They could be deterministic, but almost certainly, many of these things are going to be error prone. So really the question that what I'm thinking of when I say error analysis is how much do each of these pre-processing steps contribute to the error of the final output? Questions about the general observation here. One way of doing this is you have a really complex system. Suppose you just happen to be in this very happy, lucky situation that for each of the components, you're able to identify the ground truth. Someone gives you the ground truth label for each of these pieces. Then what you could do is systematically add more information to the system. So you could start off with your end-to-end system. That's this whole pipeline from here to here. This is the first step. And it might get some accuracy. Then you plug in the ground truth for one piece for each piece in the pipeline, so that you remove the error. And these numbers are just made up, but according to this, it suggests that really the component that's contributing maximum to the error is not your classifier, it's not your learning algorithm, it's not your features, it's actually this part of speech. If only you had a better part of speech system, then you might be able to do a better job of predicting. So really we are trying to diagnose the problem by not looking at machine learning, but by looking at what are the inputs that come in. And it is amazing how often just changing these, the inputs and giving better quality inputs gives better results. This is particularly true in the quote-unquote difficult applications like computer vision and natural language processing, but the lessons tend to carry over to other places as well. Another style of study, this is quite related, is called the feature ablation study. And this is something that I would say must be a part of every paper, every machine learning work that you do. Let's say you have invented 3 different kinds of features that you think are relevant. So, and you build a system that uses all 3 features, and you get 99% accuracy. You need to understand which of those 3 features are important. Because you can't just tell me that these 3 features together give me 99. So, if you have a collection of features that contribute to the final result, then you should try to take one set of them at a time and figure out which feature gives the most information. The reason for this is then if you're able to identify that, you might be able to get away with a equivalent classifier that's much smaller. You might be able to remove noise from your classifier. And in general, it just leads to better understanding of what makes the system work. Which means 10 years down the line, when you quit the job and moved on, and another person comes in, they might be able to actually fix bugs. Questions about ablations or any of this? Okay, so the last part of, or the penultimate part of this class is about lessons that you can use to actually take your problem that you care about and add machine learning to it. So the example that I've been tossing around through the entire semester is that of classifying fish, and say you want to do that. I'm not going to talk about how to solve this problem. That was the rest of the semester. In general, I've noticed, and from here on, these are more subjective. I mean, take things with a bit of a salt, with a pinch of salt, but not too much. There are 2 classes of solutions. One of them is this, what I call the slow approach, where you think hard about the problem, you carefully design the best features that you can find, you architect the entire system, you do everything up front, and at the end you're done. You run your system on and you get excellent test accuracy, and you are done. This is the kind of approach that leads to new research in machine learning, or new learning algorithms and such things. And a complete contrast to that is what I call the hacker's approach, where you build a brain-dead system up front with just, and it has an end-to-end, it only has the ends, right, and the insides are all mushy, and you keep iterating. The faster approach tends to work pretty well in the industry setting. It's going to get you maybe a reasonable solution pretty quickly. And my suggestion is, both of these are good, both of these are bad. What you really need is to be a slow hacker or a fast researcher, I don't know what. Just common sense that shows up in software engineering is also important in machine learning. Don't optimize too early. That is this one. Be careful of that. At the same time, don't commit to a bad path very early. I mean, this is life advice in general. A few things to watch out for. One important question you should always ask yourself when you're building this kind of system is, are you measuring the right thing? And by that I mean, is accuracy the correct thing to measure? Many of your projects have a particularly interesting situation where you might have labeled data, and maybe 90% of the examples in your labeled data, or 99% of the examples in your labeled data belong to one class, and only 1% belongs to the other class. And then what happens is your classifier could, for example, learn to predict class 1 as the output. It looks at the example, throws it away, and says class 1. What's the accuracy of that classifier? It's 99%. But is your classifier doing anything? Have you learned? Have you solved the problem? Clearly not. So you need to think about what is the right accuracy, right metric. And a very related question is your loss function reflecting that metric? Some evaluation metrics probably cannot be optimized. Ideally, the best case situation would be if you optimize the thing that you care for. If you want to minimize error, you try to minimize error. And you can't, so you come up with a surrogate. But sometimes there are functions like, in particular, the F-score is a classic example of something that cannot be minimized. F-score is the harmonic mean of precision and recall, and some of you have actually been using that. It cannot be minimized, and then you have to think about how to solve it. Something that I've been mentioning multiple times, be very, very careful of contamination. Do not let your test set bleed into your training set, because that will lull you into a false sense of security. Don't even look at your test set, because contamination can happen through you. And as a side effect, something I mentioned before, as a side point, be very suspicious of any claims of perfect classifiers on most problems. If someone claims a perfect classifier, the jump from 99.5% accuracy to 100% is too much. Most data has noise, so just be aware of that. Be also aware of the bias variance trade-off. You should know that one of the most important things you should pick up from this class is this, that you have to tread this very narrow path between underfitting and overfitting. And you should be aware of this and try to use everything that you know to combat falling into either one of these problems. Something that we saw right at the beginning of the semester, proof by pictures is not always a valid proof, because in high dimensions, the pictures are meaningless. So remember the curse of dimensionality, and don't let it give you sleepless nights, but just keep it in mind. And another thing is about all the theory. This class has definitely been more biased towards the theory of learning. And the reason for that is because the theory of learning gives us concrete grips on what can and cannot be done. Some things just cannot be learned because there is a theorem that says these kinds of things cannot be learned. But the problem is, while theory is good, and I personally enjoy it, doesn't mean that the theory is always correct. So the theory might make invalid assumptions. Like perceptron, for example, assumes that your data, if your data is separable, then the perceptron algorithm will find a separator. That's nice. Okay, give me some data that's separable then. How do you know? So this is the classic spherical cow assumptions that people make in physics. If you assume that you have a spherical cow and you know how it rolls downhill. The other thing that you might, the other kind of theoretical result that you might want to watch out for is some of these guarantees are only applicable if you have infinite data. The nearest neighbor classifier is the best classifier if you have infinite data. Okay? So you go get infinite data. So be careful of that kind of a claim as well. And really the message is you need to have experiments on real data. The theory does not, by itself, does not give you everything you need. Speaking of data, we live in the land of big data. We live in the era of big data. And that's kind of misleading because we live in the land of big unlabeled data. In general, if you have more data, more labeled examples, it's always better. And if you can somehow get cleaner training data, that's always better. So a lot of effort is spent, especially in industry, to create clean data sets with very little annotation noise or very little feature noise or things like that. And the reason all the money is spent is because the guarantees that we have get much better if your data is clean. That said, learning is impossible without inductive bias. One of the first things that we saw in the semester was if you have some, it's easy to come up with pathological examples where learning is impossible. And you need to make some assumptions. You need to inject some knowledge into your system. For example, restricting the hypothesis space. Learning needs knowledge to guide the learner, because if, for example, you are able to pick the perfect features. So really, the other big lesson that I want you to take home is that machine learning is not magic. Very often you see, especially these days, it's kind of irritating in the media, you see these news reports that talk about machine learning as if it's just a magic wand. If you have friends in the media, please teach them about learning theory. The question is, what knowledge do you inject into your system? You have been making these choices all through the semester. One of them could be, what's the right model? Maybe it's linear, maybe it's a decision tree, maybe it's a kernel, a polynomial kernel of degree 17. You're still making those choices, and somehow you bring in some knowledge that lets you make those choices. You're choosing a learning algorithm, which means you're automatically choosing some sort of objective that you're minimizing, or for decision trees, for example, you're making some choice about which learning algorithm you might use. You're choosing features, and that's one of the places where knowledge injection really shows up a lot. If you have the perfect feature, then you might have actually solved the problem. Very often, most of the time that's not there, but there's always this quest for perfect feature representations. And hopefully most of your, this lesson comes through from your experiments, from the experiment section of your homeworks. There's a question.
How do you fill the gap between machine learning theory and real-world solutions? I always feel confused for how to apply machine learning to the engineering side, specifically how to define a real-world problem and how to solve it.
So the real-world problem, so let me just paraphrase the question. The question was, how do you fill the gap between a real-world problem and what we learn in machine learning? Because there's this big gap. The real-world problem might be something like, discovering whether a DNA sequence has the potential for Alzheimer's disease or not. From there, going to actually learning the classifier or framing it as a machine learning problem is an important skill, because only then can you use all the. One of the things that we've seen throughout the semester is if someone has framed the problem as a machine learning problem, then you can use this whole library of algorithms to solve it. Then the question is, how do you go from the application to the problem framing part? And there are at least two ways of answering that question. One of them is to just go blind and build feature extractors. I know nothing about DNA, but I know that they look like alphabet soup, and I'm just going to build feature extractors that pull out these things. And once I have that, I'm going to go run around for training data and train a classifier. That is one way of doing it. But let's say we do that. Suppose one way, even then, all the considerations that we learn in class come into play. One thing we know, for example, is if you use feature conjunctions or feature lifting, then you get a strictly more expressive set of classifiers. What we do also know is those sets of classifiers need more data. So in some sense, we have some expectation of what kinds of feature transformations are prone to more variance, for example. We also know that if your dimensionality is very, very large, typically you might need more training data. So if you want to start off building this problem, you might be better off coming up with a small set of features. The other way of answering this question is to think about hiring a biologist. Very often domain experts are are quite invaluable, especially in feature engineering, because they might have spent the last 300 years figuring out the effect of this one piece of, I don't know, I guess 300 years have not gone through since DNA. So they might have spent the last 40 years talking about one specific part of the DNA or researching that, and they might know that these combinations of things are really what you should look at, and those make for good features. So don't underestimate the importance of domain experts. That said, I have to, there's an anecdote from 1980s. IBM was trying to build 1980s, 87 or 88 actually, that's before most of you in this room were born. IBM was trying to build an NLP system, and that's when they started doing these kinds of AI-driven methods for NLP in IBM, and they built a nice big team. And one thing, some guy made a comment. I mean, when I say some guy, it's actually a famous person. He made a comment: every time I fire a linguist, my accuracy goes up by 1%. So, in some sense, domain expertise is a good thing, but take it with a pinch of salt, because domain expertise might be too specific, too narrow. There is some trade-off. To go back to the question, how do you go from the application to the actual machine learning? Really, the application talks to the machine learning only through feature extraction, through data collection, and through these choices of evaluation. Each of those places, hopefully, you have some understanding of the ramifications of the choices you make. More data, always better. Cleaner data is better than less clean data. Larger feature sets tend to overfit. Smaller feature sets tend to underfit. So you're really looking for this Goldilocks spot, the sweet spot between too much and too little. And that's where all these things like regularization and such things come into play. Every time we inject this kind of knowledge, really what we are doing is we are making a claim about the nature of the problem. We are claiming, for example, if I'm doing this thing about DNA and Alzheimer's, and I extract a certain set of features, then I'm making a claim that the decision of whether this DNA expresses Alzheimer's or not is completely a function of these features and only these features. And that's a big choice that you make. Another important decision you're making is that the decision of whether this DNA expresses Alzheimer's or not is only a linear function of these features. So these are the kinds of implicit claims you're making about the nature of the problem. So it's always good to have the application in mind, even though you might be doing machine learning. Some other advice. Occam's razor says that we should learn simpler models first, and that's valid advice even in your choice of model design. Try out simple things first. If nothing, at least the simpler things form a baseline that you can then proudly stack up your classifier against. Many of you noticed or observed that ensembles tend to work better. They tend to work better, and they are often used in industrial applications because of that reason. And the one other thing about machine learning is you should think about whether your problem is learnable at all. That's an important point. Learning is generalization. So this choice of, or this decision of whether learning can actually help your problem is an important one. And it typically only comes by staring at the data and trying to figure out whether you can answer the problem. And that's where domain expertise also comes in. So one place that, I'm going to use an example of natural language processing again. Some problems are learnable. For example, if I have to predict whether, what's the part of speech of some word, it's a learnable problem because most of us, I can do it. Most of us seem to be able to do it. A problem that's not learnable is given a sentence, just a sentence, predict whether, say, this sentence was uttered indoors or outdoors. There's not enough information, and most of us will agree that this is not a learnable problem. So it's good to get this sense of gut feeling as to whether learning can even be applied here or not. And once again, that comes by thinking about the application more than any of the learning aspects. Over the last couple of years, there have been a couple of papers. Yes?
Talking about learnability, is it relevant to consider learnability in the context of probabilistic learning?
Yes, definitely. It's a similar thing. There is some probability distribution. Okay? What is learning? It's generalization, but it's also equivalent to discovering that hidden function. Can that function be discovered? Is that truly random? For example, let's take a tiny little case. So let's say I give you a sentence, and you have to. Let's say I give you a sentence, and I give you a label. The way I generated the label was I write down a sentence, I toss a coin, and I say heads or tails, and I give you only the sentence and the coin. A sentence and the coin toss. I never tell you that I even did this. Now I ask you to learn the classifier from the sentence to the label. It's unlearnable and it's probabilistic. One way of correctly learning this is if you were able to discover the underlying distribution. If you are able to discover that I did toss this coin and this is the bias of the coin, then you have a chance of mimicking me. So it does apply even for probabilistic models. It's generally true. So there have been a couple of papers in the last maybe 2 or 3 years, interestingly, coming out of industrial labs, talking about machine learning as creating a technical debt, because we are building these systems that move along so fast, and we don't care about the longevity of these systems. We don't care about this classifier might be running, say, 30 years from now, so we need to look ahead and think about the big picture, think about architecture. And one other actual minor thing I wanted to mention is there's this cool paper that I've actually listed on the website for this lecture. It's called Machine Learning That Matters. It's written by a Utah alum. And she pointed out, if machine learning was really all that good, then here's a challenge for the machine learning community, and now you're in the machine learning community. Here's a challenge for the machine learning community. Here are 6, she listed out 6 applications and challenged the community to solve them, even one of them. They're all like pretty serious things. Like number 3, machine translation, like Google Translate, helps avoid a war between 2 countries. That seems like science fiction, but that's a kind of really, really long-term view that some people are taking on this, where we are changing the way we think about computer science. Okay? I mean, this is mostly for your entertainment. You can read this and, maybe one of you will solve one of these questions. And it turns out, interestingly, each of these problems actually has machine learning systems even now. For example, clearly for number 5, IBM has been pushing out for a few years now learning-driven systems that try to not replace but help medical professionals. For a while now, a lot of cybersecurity stuff has been not happening through machine learning, but definitely people are exploring the use of machine learning. For example, to detect malware in, say, the Android App Store. And this is just the beginning, so the expectation is these things will actually pick up, at least to some level. And all these questions still remain. I mean, is this problem learnable? Is avoiding conflict or solving the oil crisis a learnable problem? And I don't even want to dare answer that question. But just to keep this in mind, you can actually dream big. So let's look back at the course. And in the last 10 minutes, I'm basically going to flash all maybe the first 5 or 10 slides that we saw in the beginning of the semester, just to convince you that we actually did something in the semester. In the first, I tried to define machine learning, and Probably the most reasonable definition that I have seen is this thing from Tom Mitchell, which talks about, I'm going to read this out, a program is said to learn with experience E with respect to a class of tasks T and a performance measure P if its performance at the task as measured according to this objective evaluation criterion improves as experience grows. Hopefully this makes more sense to you than it did on the first day of the class. The way I think about it, this E is the training set. As your training set grows, your accuracy or your F measure or whatever in the task that you care about goes up. We saw many different kinds of models, and model is just a name for what kind of a function should the learning algorithm explore. We looked at linear classifiers, we looked at decision trees, we looked at probabilistic models, we looked at non-linear classifiers, particularly through kernels, ensembles, boosting and such things. And we largely focused on supervised learning, and the setting was to learn. There is some teacher that has gone around labeling data and has given the data to you, and that's pretty much where your interaction with the teacher stops. And your learning algorithm has to figure out what the teacher had in mind. But we also, towards the end, towards the last 2 weeks or 1 week, we looked at unsupervised learning, particularly through EM, where there is no teacher. The learner only has examples and has to somehow figure out regularities in the examples. In between these two, and probably the most reasonable place between these extremes is semi-supervised learning. We have a small number of training examples because your teacher labeled maybe 10 examples, and you have tons and tons of unlabeled examples. Turns out EM can be, with minor modifications, be applied to semi-supervised learning. The labeled examples could influence your initial choice of parameters for EM. We looked at many learning algorithms. 3 broad classes. Them are online algorithms like perceptron and winner, batch algorithms like SVM, logistic regression, AdaBoost, decision trees, and all those things. And we also looked at unsupervised methods for discovering clusters in data, particularly k-means and EM. One question that I really did not answer, but kept talking around, was the importance of representation. Features are important, features are not only important, but really make or break your classifier. Good features give you a good classifier, bad features really leaves you with no hope. One thing which we did not sadly get to cover was discussion on dimensionality reduction, which takes large feature sets and tries to reduce them to lower dimensional sets so that you can capture the most important features without paying the price of dimensionality. But you should take a look at the slides, they are online, I think. If not, I'll put them up. Really, the class was entirely structured around the theory of learning. Throughout the semester, we kept trying to answer the question of what is learning. Turns out that there's no one answer. We tried to answer it in 3 different ways at least. One of them being online learning, where we said learning is when the classifier stops making mistakes. Another one was batch learning, where we defined, or pack learning, where we said that learning is when the classifier, given a training set, generalizes or has low error on future examples. Finally, we also looked at Bayesian criteria for defining learning, maximum a posteriori learning or maximum likelihood learning. Really, the main pieces that we are juggling deal with representation. Representation could be both representing examples and representing classifiers. It deals with evaluation, namely, what is good enough? Accuracy, or we only looked at accuracy and margin, but a little bit at square error and posterior, the probabilities and stuff, but there are other measures. And given a choice of this classifier, this features, and this way of evaluating, we can throw in different optimization algorithms. We have clearly not covered all of this. This is just a slide from a paper by Pedro Domingos, who, by the way, recently wrote a book called On Machine Learning, and it's a pop science book. It's not even technical. Though I have not read it, so I don't know if it's good enough. If you guys read it, let me know if you like it. But really the main questions that we've been looking at deal with representation, defining good, and optimization. I've complained about this many times in my office hours. It's a shame that this is only one semester class because there's so much we did not cover. I mean, huge amounts of stuff, but hopefully what we did see builds the foundations that lets you pick up books or papers in these other topics and spot what is the interesting contribution. The focus of this course was mostly on the fundamental concepts and the algorithmic ideas, and which means that I did not necessarily spend any time on a particular, actually I didn't spend any time on any machine learning tools, and I have been actively discouraging people who came to me saying that they want to use a particular tool for their homeworks or projects, partly because you are supposed to be writing those yourselves. We did not focus on any one particular learning paradigm. Hopefully we've got some common language to think about learning algorithms, to spot what is interesting. So just to summarize, we saw this broad technical overview of many different learning algorithms and learning strategies. I hope that through the homeworks you've got this ability to implement learning algorithms, and most of you have actually done really cool stuff. And interestingly, the choices that you made, if you want to think about it, you might want to, if you had to revisit the design choices that you made in implementing your learning algorithms, you might think about how you would change it so that you can build a big learning library or something. And one skill that really comes up by doing really is to identify where machine learning can apply, and if so, how to use it. And this really only comes by doing. So not sure if this is a learnable concept of whether machine learning applies. And instead, I try to give you a lot of information about many, many different things and their relative strength and weakness so that hopefully you can make the choice. So, go out there and set fire to the world. All right, I'm going to stop now. And, yes?
Sorry, it's about the project.
Okay.
Do you want an IEEE style? Or?
I don't care. Just stick to the page limit and remember that I'm a human, which means I have to read 60 project reports within about 3 days. So be kind to me.
Do you want the software design or just the concepts, the testing? Is there anything you want to focus on?
All the choices that you had to make.
Okay.
I don't want to know what's the name of the function in your code that actually does something.
Yeah.
I really don't care. Those are like arbitrary choices, but all the relevant choices that you had to make. Design-wise, all the relevant choices that you had to make from the point of view of learning, why you chose this feature set over that, why you chose this algorithm, what's the reason for any decision that you made, and what if you had more time, if you had another whole semester to start from scratch, and if you had known about machine learning right at the beginning, how would you have gone about it? All right, we should stop now. Please show up for the exam. It's going to be fun. And I'll see you on Wednesday.